I'm very excited to be here. Thank you to Sarah and Alfred for inviting me to do the colloquium. We'll talk about solar science with the MWA. We'll start off with some background on the MWA instrument, what its science goals are, and how it fits into the historical context of low-frequency imaging observations of the sun. Tell you a little bit about how to access and reduce the data, and then give some background on the different solar emission mechanisms that are relevant to the observations that I'll show you. While we're going through the background slides, we'll also highlight a number of the results from other people in the solar collaboration. And then we'll get into the three main projects that I've worked on so far with the MWA data. The first two have to do with a specific type of solar radio burst, and then the last one has to do with spectropolarimetric imaging. All right, so the MWA is a low-frequency radio interferometer in Western Australia. We're looking here at drone footage from the core of the array. And each of the squares that you see is a 4x4 grid of dipole antennas. So we call those a tile. And each tile is its own aperture array. And then the full MWA is comprised of 128 of these tiles. That was in the phase 1 configuration, at least. Now, as of around a year and a half ago, we actually have twice as many of these tiles, but the solar collaboration hasn't yet done much with the phase 2 data yet. So everything I'll show you today is from phase 1. So the MWA is not a dedicated solar instrument. It has four main science themes. So the first of which is to do with the epoch of reionization. So they would like to detect a signal from the redshifted 21 centimeter line of hydrogen after the first galaxies formed and started to reionize the intergalactic medium. So that's a signal that lots of groups around the world are trying to detect and nobody's done yet. Then it's a wide field imager, so survey work is really important to it. The extragalactic surveys in particular have probably been the most significant science output so far in terms of publications and citations. And then time domain astrophysics is things like pulsars and fast radio bursts, also flares from other stars. And then the solar, heliospheric, and ionospheric science is lumped into one group. We call ourselves the SHI collaboration. And I won't say too much about the ionospheric side, but I wanted to give one highlight from that. So the image that's on the right there is an image of density ducts in between Earth's ionosphere and plasmasphere. So the alternating pattern, the stripy pattern that you see is alternating high and low density regions that are aligned with the geomagnetic field. So that's what the black lines are. And these ducts had been predicted to exist, but there had been fairly limited observational support for them. And this has probably been the most significant ionospheric result to come out of the MWA so far. Then other people in our SHI collaboration, they're interested in interplanetary scintillation, which I'll say a little bit about in the next couple slides. Also Faraday rotation measurements of CMEs as they propagate through the heliosphere. And then the direct solar observations is mostly what I work on. So I wanted to say just a little bit about the IPS stuff because we have some very recent results that I thought would be of interest to this audience. So interplanetary scintillation is when variations in the solar wind density cause background radio sources to twinkle. So it's very much analogous to why stars twinkle as their light passes through Earth's atmosphere. So this is just a GIF animation of some radio sources twinkling as seen by the MWA. And so you can learn stuff about the solar wind speed in particular with these IPS observations, and you could potentially also see the effects of a coronal mass ejection move through across your IPS field. And so that's something that we've been trying to do. Here's an example of a coronal mass ejection observed by the LASCO coronagraph on SOHO, and then projected into one of the IPS fields of view. So this dotted box is where the MWA was looking, so it's around 30 degrees away from the sun, and the black arc is where you expect the front of the CME to be given the speed that it was observed with in the LASCO observations. And just very recently, over the last week or so, our collaborator John Morgan at Curtin University in Perth has found what seems to be like a band of enhanced scintillation where we expect the CME to be in the MWA field of view. So this plot on the right shows the scintillation index, which is sort of how twinkly are the objects, for when the CME is there, divided by when the CME is not there a day earlier. And you see a band of lighter colors here in the middle, and we think that that's due to the CME passing along. So this is exciting. This is also the first step toward making Faraday rotation measurements. So one of the main objectives of the MWA is to try to look for linear polarization or linearly polarized background sources occulted by a CME. And so as the linearly polarized emission moves through the CME plasma, the magnetic field of the CME will change the polarization state. And if you measure that, you could potentially work out what the magnetic field strength and orientation of the CME is as it's moving through the heliosphere. So that's one of the main goals for our collaboration, and this is a big step in that direction. So now moving to the direct solar observations. One of the reasons why the MWA is an interesting and exciting instrument is because there hasn't been a lot of coverage of the frequency range that we're interested in. So really just a handful of telescopes throughout history have made images of the sun in this regime. So the earliest of which was the Colgora radioheliograph. So not the earliest to make an image, but the earliest one that could make an image of the Quiescent emission. And so that was between 1967 and 1984. And then there was the Clark Lake radioheliograph a little bit after that. The Gwari Beta Nor radioheliograph in India is still operational and does some polarimetric observations as well, which is great. And then the Nancy radioheliograph is probably the one that most of the people in this audience have heard of. That's a dedicated solar instrument and has done a lot of work on a variety of topics. And then the MWA, between 80 and 300 megahertz, came online in 2012, and also LOFAR came online just around the same time. So LOFAR and MWA are sort of the next generation of low-frequency telescopes. LOFAR as well is not a dedicated solar instrument, but does do solar observations. And they are similar in a lot of ways, have a lot of similar goals, but there are some differences between them. The MWA is a much more compact array, which gives it an advantage in terms of sensitivity. LOFAR is much more distributed. There are stations around Europe, so potentially you could get higher resolutions, and LOFAR has a bit faster time resolution as well. So that's our historical context. MWA data, unfortunately, is not public immediately. It only becomes public after 2 years. We do have a lot of solar data in the can, though. Around 3 petabytes have been collected, but less than 1% of that has actually been turned into science-ready images. And there are currently 2 independent data reduction pipelines to produce images. One that I developed, which is based on taking the techniques and codes that are used for some of the night sky observations, specifically the extragalactic surveys, and working them into a form that's good for the solar observations, and then one that's more recently been developed and specifically tailored to doing the solar observations. So here's an image comparing the results from the 2 different pipelines. So we're looking at our lowest frequency there, 80 megahertz. The solid circle in the center of each panel represents the photosphere. And the pipeline that I developed is on the left-hand side that uses a software called WS-Clean. And then the solar-specific one is on the far right. That's called AirCars. And that was developed by Surajit Mondal and Divya Oberoi at the National Center for Radio-Astrophysics in India. So during quiescent periods, the 2 data reduction methods give very similar results. AirCars, though, allows you to achieve much higher dynamic ranges. So the image on the bottom here is the highest dynamic range image that we've yet achieved with the MWA, so a factor of 74,000. And that's during a really intense radio burst period where the important thing is with the finer calibration that you can achieve with that pipeline, you can also still distinguish the thermal emission from the disk of the sun, which is the stuff in here. The WS-Clean pipeline that I developed still has some advantages, though, over the AirCars, namely that it can do the polarimetric calibration, which isn't yet possible with AirCars. So it is a bit of a chore to reduce the data. It's not super straightforward to just download it and install the software and do it. So we have 2 proposals right now one in Australia and one in the States to try to reduce a significant fraction of our data archive and then reduce science-ready images to the broader community so you don't have to reduce those yourself. So hopefully over the next year, maybe 2 years, you should start to see publicly available images that can be used by the community. Okay, so now we'll get into the emission mechanisms that are relevant to our observations. So the quiescent emission from the sun at low frequencies is dominated by the thermal Bremsstrahlung process. So that's just because the corona is ionized, and as the ions and the electrons deflect off of one another, mainly the electrons deflecting off of the ions, they produce a bit of radio emission as they do. So here are images at 6 different frequencies that are dominated by Bremsstrahlung. So I'll use this image to also say a little bit about how the solar observations with the MWA are typically done. So here we have our lowest frequency, 80 megahertz, is on the upper left, and then our highest frequency that we typically use for the solar data is on the lower right, 240 megahertz. That's basically our full bandwidth, but the instantaneous bandwidth is only about 30 megahertz, and you can distribute that however you want across that 80 to 240 range. So typically we use a picket fence mode where we have 12 or sometimes 24 contiguous channels that are distributed across that frequency range. So this is just showing 6 of them. You'll notice a couple things. Again, the solid circle in the center is the optical limb, the photosphere, and then the ellipses in the lower left corner of each panel represent the synthesized beam size. So that's essentially the resolution element. And at 80 megahertz, you notice that the sun is quite a bit larger, puffier, more extended than it is at 240 megahertz. And that's because the Bremsstrahlung emission at lower frequencies is produced at larger heights above the surface. And that's related to the background density. Okay, so that's a thermal background. That's what the sun is always doing. And then on top of that, you can have spikes of non-thermal emission due to this plasma emission mechanism, where electrons are accelerated. They can be accelerated by a number of different means, and they induce oscillations in the background plasma. Those oscillations are called Langmuir waves, and then the Langmuir waves ultimately produce radio emission, either by scattering off of ion sound waves. That gives you emission at the fundamental plasma frequency, which is proportional to the square root of the background density. Or the Langmuir waves can then again be scattered by other Langmuir waves, coalesce, and give you emission at the second harmonic of the plasma frequency. So here's an image from the MWA during a type 3 radio burst. So this is caused by this plasma emission mechanism. And the important thing to note here is just that this mechanism can give you brightness temperatures or intensities that are orders of magnitude larger than the thermal emission from the sun. Okay, so all the main solar radio burst types are thought to be caused by this same plasma emission mechanism, although exactly how you accelerate the electrons in each case is different, and in some cases is still unknown. So solar radio bursts are defined by how they appear in so-called dynamic spectra. This is sort of like the bread and butter of solar radio observations. You have time on the x-axis and then frequency on the y-axis. So all of these types were defined by how they appear in this representation before there were imaging observations available and before we really knew what the different types were associated with in terms of activity on the sun. So type 1 bursts are what we're looking at up at the top. These are these narrow band spikes. Sometimes there'll be continuous emission associated with them. Might persist for a number of days. They're associated with active regions as they transit the disk. Although type 1 bursts are a bit mysterious because you'll often see an active region with really strong, robust radio emission, and if you go and look at the same region in other wavelengths, say in the EUV, you might see nothing. So it's not clear what is accelerating the electrons for type 1s. The main ideas are either little reconnection events or shocks at the front of upwelling waves. So that's type 1s. Type 2 and type 3 bursts, though, have much more well-defined associations. So type 2 bursts are associated with the leading edges of shocks in front of coronal mass ejections. So that's where the electrons are accelerated. This is an example of a type 2 burst, and it will start at a higher frequency, and then it will drift down to a lower frequency as the shock propagates outward through lower and lower background densities. That gives you lower and lower frequency radio emission. So type 2s are defined by that slower drift rate. And so this band up top would be the fundamental emission, and then this would be the second harmonic. And then type 3 bursts are similar in a sense. They also start at higher frequencies and then drift down to lower frequencies. for the same reason, but they're instead excited by beams of electrons that are accelerated by magnetic reconnection. They're often associated with X-ray flares then, and because these beams are moving at a significant fraction of the speed of light, usually around 0.3, 0.4 c, their drift rate is much more rapid than it would be for the type 2 burst. So those are the main types of solar radio bursts. There are a few more types, and the types have subtypes, so it does get a bit more complicated than that. But they're quite intense. And in addition to these intense radio bursts, you can also produce weak non-thermal emission, and this is something that the MWA in particular has contributed a lot to. So this is an example of a dynamic spectrum from the MWA, and what they'll do is do a boxcar average to get the component of that that's varying slowly, and then they'll subtract that from the original to get the impulsive component. And this plot on the right is showing, as a function of frequency, the amount of flux that's being contributed by the slowly varying component as opposed to the impulsive component. And the idea, or the point here, is that even during what you would think of as a moderately quiet or quiet period, there are still a lot of these impulsive events. And as much as 50% of your emission might be due to this plasma emission mechanism, even if you're looking at what you think is a quiet period. And so that's something that hadn't been appreciated before the MWA observations. The source, again, of these non-thermal electrons is not clear. Rohit Sharma and his collaborators, mainly Divya Oberoi, in these two papers, suggest that the spectrum that they see is consistent with nanoflares. Okay, so that's all plasma emission. Now, the last emission mechanism that we maybe occasionally have to worry about or think about is synchrotron or gyrosynchrotron emission. And so those are due to near relativistic, or relativistic in the case of gyrosynchrotron emission, electrons that are moving within the expanding magnetic field of a CME. So they may, in rare cases, produce low frequency emission. There's really only been 4 or 5 instances of this known, and we think, or our collaborators in India think, that they have detected the first one of these types of events with MWA observations. And this would also be the first event that's not been observed by the NANCA radioheliograph. All the previous examples were with NANCA. So this image is an MWA image round about the time that a CME is occurring. And the idea is that this circle is where the CME is interacting with a streamer and then producing this gyrosynchrotron emission. And so this is a fit that they've done to the radio spectrum. And the neat thing about gyrosynchrotron emission is that you can use it to estimate the magnetic field strength at that location. So it's a powerful diagnostic of the magnetic field if you can detect it. An interesting thing about it, though, is in all of the radio examples where they think that they're detecting gyrosynchrotron emission, it's not clear, again, how you've accelerated electrons, why you have this population of very fast-moving electrons. And so that's interesting. All right, so now we're going to get into some of the things that I've been working on specifically. So my strategy with working with the MWA data has really been to just reduce as much of it as I can, and then look at what we find. And so one of the events that caught our eye early on was this one. This is a type 3 burst. And if we look at the upper left plots, those are dynamic spectra. So the MWA's spectrum is up at the top, and then the Kolgora and Leamonth solar radio spectrographs are on the bottom. And so those observations were actually used to detect the burst, which sort of triggered my reducing of this particular observation period. And the interesting thing that I want to draw your attention to is just in this middle panel up at the top. So that's the 80 megahertz intensity. Each time step is a half second, and we are looking at just about a minute of data here. And you'll notice that as the burst begins, it starts out as a relatively compact source, and then it quickly diverges into these two components. And that splitting happens repetitively over and over again during this period. So here's some still frames of that at a little higher frequency at 108 megahertz. Again, we have this splitting into two components. Each of these episodes lasts just around 2 seconds. And if you take the slit that's drawn in the in the first panel, and then take the emission along that slit as a function of time to make your distance time plot. This is what you get, and you can measure the plane of sky speed, and we find speeds for this thing of around 0.1 to 0.4 times the speed of light. So that's very much consistent with the speeds that you would expect the electron beams to be moving at, but it's not, given the structure that you see in the different frequency channels, that's not the direction that you would expect the electron beams themselves to be propagating in. You have to think a little bit harder about what's producing that splitting motion, as opposed to just interpreting it as the direction that the electrons themselves are moving in. So to try to untangle that, we turn to the extreme ultraviolet observations. So this event is associated with a C8 flare, so a moderate flare. On the left-hand panel here, we have a movie of extreme ultraviolet jets that were observed by the Atmospheric Imaging Assembly on the Solar Dynamics Observatory immediately after the radio burst, so over about a 20-minute period, beginning right with the bursts and then carrying on afterwards. So it's a little bit hard to see up on the screen, but the middle panel is a running difference, so each frame subtracted by the previous one, and then the final frame is a persistence map where we add up all the differences to sort of collate the jet trajectories into a single image. And so if we take the last frame of that persistence map movie and add a little bit of additional processing, this is what we come up with. And I think it nicely illustrates the magnetic field configuration to some extent of this region. And the idea is that the EUV jets are going to be moving along very similar, if not the same, magnetic field structures as the electron beams that excited the Type 3 bursts. And this particular structure is very reminiscent of magnetic field models of coronal null points, where you have these very strongly diverging field regions, which are often called quasi-separatrix layers, diverging around a null point. So the null point in this case would be in here, and then these fields would diverge on either side of it. So here are some models of sort of similar configurations. This would be low down in the corona, and this would be a similar structure viewed much higher up, where SC here stands for separatrix curtain, and that's what we think these field lines here are analogous to. So if we take the radio contours and we overlay those on top of the EUV image, this is what we find. So we find that our two sources, the northern and southern components, are distributed on either side of the what we would think is the separatrix spine, which separates field going off in two different directions. So combining what we know from, or what we interpret from these two observations, we come up with a cartoon picture that looks like this. We think our electrons are accelerated at the flare site, which is here in the cartoon, here in the image, and then the beams move along mostly parallel magnetic field lines until they approach the null point, at which point they diverge and head off in different directions. And so the point with the Type 3 bursts is that the emission is only generated when the beams pass through a region of a specific density, which generally corresponds to a specific height above the surface. So the beams that are moving closest to the center are going to arrive at that height first, and then the beams that are moving a little bit along adjacent field lines are going to get there a little bit later and a little bit later, and this is what we think is producing that splitting motion. At least that's the model that we came up with to explain it. Okay, so that's all I'm going to say about this project. Now I'll say a little bit about using Type 3 bursts to probe the density structure of the corona. So I've already mentioned that the emission mechanism, the plasma emission mechanism, is very intimately tied to the background density. So you get radio emission at a frequency that is proportional to the square root of the density. So in principle, if you know where your emission is coming from and you know the emission frequency, and you can know or make an assumption about whether or not it's fundamental or harmonic emission, you then have a very good estimate of the coronal density, at least in principle. So that's what we tried to do here. We've have data for around 50 of these events, and we chose the 3 of them that are right at the limb with more or less radial trajectories. So the grayscale is showing the thermal, or the quiescent background at our highest frequency, 240 megahertz, and then the colored contours are the burst sites. So each of these bursts happens to be associated with a white light streamer observed by LASCO, and you'll also see a little bit of activity in very thin EUV rays that are hard to see in this image, but are also more or less aligned with the path of the radio bursts. Yeah, we're just going to take the positions, interpret those as the height above the surface, and then look at what the implied density profile would be. So very straightforward. This is what we get. So height is on the x-axis there, and then electron density is on the y. So the upper three curves with the squares and the dashed lines, that's what you get if you assume fundamental plasma emission. And then the lower three with the circles and the solid lines are what you get if you assume harmonic emission. In this case, we actually can't distinguish with the observations between fundamental or harmonic. It's something that is possible to do, but you'd need finer time resolution than we have with the MWA. So if you assume the harmonic emission, the densities imply enhancements of around 2.5 to 5.5 times that of standard background models, which is consistent with the densest models of streamers that you can find in the literature. So that's what the black line is. That's a dense streamer model, and then the dotted and the dashed are two different background models. So this is not a surprise. This result had been obtained from previous generations of instruments and is also consistent with more contemporary data. So this is comparing all results to work from higher frequencies from Bin Chen. These are the asterisks up here. That's using VLA data. And then also lower frequencies using LOFAR down here, which was done by Diana Morrison in 2014. And so all of the density profiles are reasonably well fit by this offset power law model that my supervisor, Iver Cairns, is a fan of. So there are really two main interpretations for why type 3 bursts imply densities that are big. One of them is that you just believe the densities and that the beams are moving along particularly dense structures, or at least the beams that produce observable emission. This was the interpretation that was favored early on, in part because type 3 bursts are often associated with streamers, as I showed you. Also, if your emission is produced in a relatively dense region, when it propagates out into a less dense region, it's much less likely to be absorbed or scattered. However, later authors came along and showed that there are a number of propagation effects that can also shift the position at which you're viewing your radio source from where it was actually emitted. So one of the more interesting ones is called ducting, where your radio waves are bouncing along in an underdense flux tube. It's almost like a fiber optic that delivers your radio emission to a larger height, at which point the walls of the duct become sufficiently low density that the emission can then escape. So that's a strong theoretical concept, although it's hard to believe that that's happening in all of these examples, that enough of these ducts exist. But it turns out that you can get a similar effect by random scattering against the high density fibers that we know permeate the corona from coronagraph observations, for instance, during eclipses. So because these high density fibers are not randomly arranged and they're mostly radial, random scattering against them will also tend to shuffle the radio emission out to a larger height, which you then observe it at. And so that's the other interpretation for why the radio bursts tend to imply quite large densities. So to try to investigate this to some extent, I wondered if the extent of the quiescent emission from the corona is related. So the extent of the corona tends to be larger at lower frequencies than you would expect from your model predictions. And the standard explanation for this is also scattering against density and homogeneities. So at the top panel here, we have MWA images from 5 different frequency channels for one of our events, and then below that is a forward model using Sarah Gibson's forward code and the magnetohydrodynamic outside of a sphere MAS model from the predictive sciences group. And what I wondered is if the extent to which the corona is extended in the observations beyond the model predictions, is that similar to the height augmentation of your radio bursts. So to check that out, we looked at how the intensity profile in the model and in the observations fall as a function of height. And so that's what the plot on the lower left is showing here. And if you just go to the height of the radio burst in the model and grab the normalized intensity in the quiescent image and then go back to that same normalized intensity in the model image, that gives you this delta H offset. And it turns out that for at least two of our events, the height offsets between the modeled and observed quiescent emission is very similar to the extent to which the radio bursts are seen at a larger height than you expect from a standard background model. And then for one of them, it's not. So we suggest that the radio propagation effects, namely scattering, can largely, but maybe not entirely, explain these density enhancements. And you would want to do some different calculations, mainly ray tracing, to investigate this further. So that's all I'm going to say about that. Now for the last 10 or 15 minutes, I will tell you about the stuff I'm working on now, which is spectropolarimetry with the MWA. So both of the dominant emission mechanisms, the thermal Bremsstrahlung and the plasma emission processes, produce circular polarization signatures. So the plot on the right there is showing the dispersion relation for waves in a magnetized plasma. So the electromagnetic modes are the ones up at the top. So those are the X and the O modes, which stand for the extraordinary and the ordinary modes. And so both of these are 100% circularly polarized with opposite senses. So circular polarization is when the electric field vector of your wave is rotating in a direction that's perpendicular to the direction of travel. And for so the X mode, the electric field vector, is rotating in the same direction as the gyro motion of the electrons around the magnetic field. And so the two modes are produced at different levels depending on which emission mechanism you're seeing. So for thermal Bremsstrahlung, it very slightly favors the X mode. And then for plasma emission, it heavily favors the O mode, 100% for fundamental emission. So that is what is producing the circular polarization signatures that we're going to see, either one of those two effects. It does get more complicated. The polarization state can change if the emission is passing through a region where the magnetic field is perpendicular to the region where it was generated. Also, the X and the O modes have slightly different group velocities, so they have slightly different refractive indexes, so that can give you some separation. And then also scattering, which we know is important, tends to reduce the polarization fraction. So those are all complicating factors. So here we have some polarization images from the MWA. The exciting thing about the MWA is that it is the first instrument where we can make spectropolarimetric observations at these low frequencies of the quiet sun, and even of active regions that are not bursting at a particular time. Previous instruments, like, for instance, the NANSEI radioheliograph, could make circular polarization images, but they had only enough sensitivity to do so during intense radio burst periods. So they could not probe the quiescent structure, which is what we're trying to do now. So we'll start with the image that's at the top middle. So that image is suggesting to us that the whole sun is circularly polarized with one sense at a level that's greater than 0.5% everywhere. And so we know that is not true. The thermal Bremsstrahlung should not give us that signature. And this is an instrumental effect, an artifact of our calibration that needs to be dealt with before we can actually use these data. So we call this leakage, where errors in your primary beam model, in how you think your instrument responds to the sky, produces an effect where some of the total intensity, the Stokes I signal, leaks into the circular polarization, the Stokes V signal. So this has been sort of well investigated for the astrophysical studies. They're typically doing very wide field images where they have lots of sources in their field, and they'll take the known unpolarized sources and use that to fit a surface across their whole field to subtract out this leakage. And from their work, we know that on the quite small spatial scale of the sun, at least for the MWA purposes, the leakage fraction shouldn't vary. and also on the timescales of a typical MWA observation, which is around 5 minutes, also that fraction shouldn't vary. We don't have, with the solar observations, background sources where we can measure the polarization of a particular source because we can't detect, at least not in these data, background sources in the vicinity of the sun because they're too faint. So in order to subtract out this leakage, came up with a statistical approach that relies on the fact that the thermal Bremsstrahlung process should be giving you low polarization fractions, and over your whole image, most of your pixels should be polarized to less than 0.5%. So we minimize the number of pixels that have a polarization fraction greater than that. And that's what this plot at the top is showing. So this is just a grid search that looks for the fraction of Stokes I that you can subtract to minimize that number of pixels above 0.5% circular polarization. And so for in this case, we have a leakage fraction of negative 12.5% or so. And so once you subtract that off, you get this image here on the right. And so that compares very well to another frequency channel from the same observation, which seems to not suffer from any leakage at all. So we're able to recover the same structure that was previously hidden beneath this leakage effect. So that's one example. Here's another example of a similar thing where we have pretty strong leakage in two different frequency channels of opposite signs. And then when we apply this algorithm, we recover basically the same structure seen in both frequency channels. The examples that I'm showing you here are pretty severe. Typically, this effect is down around 1% or so. So that's something that needs to be done for all of our data before we can use this polarimetric stuff at all. Okay, so having said that, one of the most interesting things, I think, to jump out of the polarimetric images so far has to do with coronal holes. So coronal holes are low-density regions where the magnetic field is open, and in the total intensity image, Stokes I, that's on the left here, this is our coronal hole right at the center, the little dark bit. And one of the other interesting things at low frequencies is that when you go down in frequency, your coronal holes, at least ones near disk center at low latitudes, will often become quite bright structures. And this is something that had been known from a small number of previous observations, but hadn't been characterized in quite the same detail as we can now do with MWA observations. We think this effect is to do with refraction at the coronal hole boundary, bringing in some of the emission that's being produced outside of the coronal hole. And there's another PhD student named Mojibur Rahman at University of Sydney who's working on that aspect. Another thing that we see with the polarization, though, so the circular polarization is the left-hand panel, is this ring structure where we have one polarization sense surrounded by a ring of the opposite sense. And so we see that at most of our frequencies for this event, and then this other coronal hole shows a very similar structure, but the signs are all flipped. This is a peculiar signature. We were quite worried initially that this was some sort of instrumental artifact. We've done a fair bit of digging to try to ensure that that's not. And we see a similar thing, or we've detected this in around 28 observations of 13 different coronal holes in 2014 and 2015. So we're pretty confident that the structure is real. Now we have to try to figure out why it's happening. So this image overlays contours of the polarization onto some other data types. So in the second column, we have an EUV image from AIA. So it's maybe a little bit hard to see the contours of the polarization, but they're right on top of the coronal holes where you want them to be. And then the third column shows the line of sight magnetogram from HMI. So these two coronal holes have opposite magnetic field configurations, which is makes sense given that they have opposite polarization signatures in the radio data. And then the last column shows the line of sight component of the magnetic field in a global potential field source surface model. And the strange thing about these observations is that the central polarized component does not match the sign of polarization that you would expect from thermal Bremsstrahlung, given the magnetic field configuration. And we don't know why this is yet. We have two explanations, or two guesses. So one is to do with propagation effects. I've already mentioned that the X and the O modes have different refractive indices. So potentially, propagation effects, refraction, could give you some separation of the two modes. We're not really clear on how that would work exactly, though. We need to do some ray tracing calculations to try to suss that out. Another idea that occurred to me really just a few days ago, and maybe doesn't make any sense at all, but I'm hoping that somebody here might have an opinion, is maybe we're seeing very weak plasma emission from network jets deep near the base of the corona in the transition region. When we're looking inside a coronal hole with the MWA, the emission inside the coronal hole, because the densities are so much lower, are being produced, the emission is being produced at a much lower height. So we're really down at the base of the corona, or maybe in the transition region at our highest frequencies inside the coronal hole, whereas outside we're well above that. So one of the significant results from the IRIS instrument are the discovery of these network jets, which exist all across the sun, but as I understand it, are particularly common and intense inside coronal holes. So if you have very weak plasma emission from these things, that could flip your polarization sign, even if your total intensity spectrum is still dominated by thermal Bremsstrahlung. And that's because the circular polarization signature that you get from plasma emission is 100%. So you don't need to be dominated by that emission mechanism to give you a weak polarization signature opposite of what you expect from Bremsstrahlung. So the question I would have for anyone who knows about these jets is, to what extent can they accelerate non-thermal electrons? That would be the question. If they can't accelerate non-thermal electrons, then they can't produce plasma emission. Okay, so that's coronal holes. The most common type of feature that we see in these circular polarization images are relatively compact sources around the size of the beam. Developed an algorithm to automatically pull these things out. Got around 800 of them in 1,200 observations or so, and all of these are detected in at least 3 different frequency channels. And the interesting thing that we have is a positive correlation between the total intensity and the circular polarization fraction. So as the things get brighter in total intensity, their polarization fraction also tends to increase. And the highest intensity, highest polarization fraction sources are almost certainly type 1 bursts, or noise storms, which is the first example of radio bursts that I described at the beginning. And so they have high polarization fractions because, again, they're caused by this plasma emission process, which has a very high polarization rate. And in this plot, we don't see any separation between these high polarization, high intensity sources and the lower polarization, lower intensity sources, which were not detectable with previous generations of imaging instruments. So the question is the emission mechanism the same for all of these sources or not? Right now we think that, yeah, it probably is. It's probably plasma emission for all of the objects, but for the very weak sources, again, like I was talking about in the previous slide, you're probably still dominated by Bremsstrahlung, but there's a plasma emission source in there that's doing just enough to give you a weak polarization signature in the opposite direction. And that could be because it's just weak, or also the site of the plasma emission is small relative to the beam size, which gives you this beam dilution effect. So that's what we're thinking there, although we're not totally sure. Okay, so that's all I'll say about those. Oh, these are associated with active regions, I should say. Last thing, this is the last slide before the conclusions. We're trying to investigate the large-scale quiescent structure and have a look at what the polarization can tell us about the large-scale magnetic field of the sun. So on the left-hand column here, we have Stokes I total intensity images for 4 different days that are not dominated by one of these really intense noise storms. And then the second column is circular polarization. Third column is the polarization fraction. And then the last column, again, is the line-of-sight component of the magnetic field in the global PFSS model. What we find is that at the lowest frequencies, the boundaries between opposite polarization signs correspond reasonably well to the locations of polarity inversion lines in the model. And this is something that we could not probe with any previous instrument. So that's all well and good at higher frequencies, or at lower frequencies, excuse me. This is 89 megahertz. If we go to higher frequencies, we do not see the same correspondence between the line of sight field and the polarization fraction. It's all jumbled up, and we're not really clear yet on why that is, if that also has to do with this mixture of Bremsstrahlung and plasma emission, for instance. One of the things that we've been working on over the last few days is trying to use Sarah's forward code to forward model the Bremsstrahlung emission, specifically for the lower frequency emission, and we're finding that indeed we can do a reasonably good job at reproducing that lower frequency signal. The higher frequencies haven't really looked at yet, although I think those are going to be much more challenging. Okay, so now onto the conclusions. We've observed some new things to do with type 3 radio bursts, and we think we can explain them in terms of electrons diverging along divergent magnetic field structures. We don't really know yet how widely applicable this model is. So it seems like there are other events that we have data for which this type of model would work, and there's at least one observation where I'm pretty sure it cannot work, and that's interesting. So what would be giving you that similar motion in this other context? Type 3 bursts imply large densities, and this is something that had been known before, so it's not exactly new, but radio propagation effects are contributing significantly to that, but maybe cannot fully explain the enhancements that we're seeing. And then spectropolarimetric imaging with the MWA offers a new and unique tool to probe the magnetic field of the sun on scales and heights that are difficult to access with other instrumentation. That's really exciting, but there are a lot of unanswered questions that we have at this point. So how do we explain that ring structure that we're seeing in the coronal holes? Is the emission mechanism the same for all of those compact polarized sources? And can we successfully forward model the large-scale quiescent emission? As I said, at least at low frequencies, we think probably yes. Higher frequencies remains to be seen. As I said at the very beginning, the MWA has collected a ton of data, and very little of it has actually been reduced into images. So there is a really wide discovery space, and even in the data that I have, so I have a database of 4 or 5 million images, and there's a lot in there to pull out. One of the neat things that we saw really just last week is this event where we think we're seeing the signature of a coronal mass ejection in the MWA observation. So this is just below the occulting disk of Lascaux, and this is the CME about 10 minutes after this observation. And this would be one of the nicest images that we have of a CME at these low frequencies, really in radio observations in general. But the puzzle is we don't really understand why it should produce emission so intensely. So there's a lot of unanswered questions. There's a very wide discovery space, and you should look forward to a number of things to come from this instrument in the future. So thank you.
We have time for questions. Sarah.
Thank you, sir.
Can you say something about the, so when you're looking at your Stokes V circular polarization in the Quiescent corona, and you've got something which you can kind of compare to the potential field, line of sight magnetic field, how would that compare to the sort of thing we would hope to get from Cosmo, which would also be a global field, and there you'd get the optically thin integration of the line of sight weighted by the plasma along the line of sight. There's different effects going on with the radio, right, where you've got optically thick surfaces, and so can you say a little bit about like how they complement each other?
Sure. So I don't know very much about the Cosmo data or what it will be, but the emission or the mechanism that's producing the circular polarization signature is totally different in the two instances. And so as Sarah was saying, with the radio data, we are, at least at the low frequencies, right at the boundary between optically thick and optically thin, and that depends on where you're looking, if you're on disk center or off disk center, and the circular polarization fraction that you get will depend on how deep along the line of sight you're looking. So if it's optically thick, you'll get something different than if it were optically thin. The circular polarization in this case is being produced by the thermal Bremsstrahlung process, which is related to the magnetic field strength. And I think in Cosmo it's due to splitting, right? Or Zeeman splitting or the Hall effect, or I'm not sure what it is. So these are two totally different mechanisms where you can probe the magnetic field, hopefully in similar regions, and hope to find some correspondence between them. Yeah.
What else?
You said you're preparing a reduced data product.
That's the hope, yeah.
And how many images are we talking, and what sort of time frame are we talking about when this reduced data will be available?
Right, so we have two compute time proposals, one that I submitted to a cluster in Australia, and then one that Colin Lonsdale at MIT has submitted for reduction in the States. So I've asked for 5 million core hours to reduce data. The archive that I have currently was done with 1.5 million core hours, and that gave us an archive of around 4 to 5 million images. And so those are each half-second images. What we're hoping to do with, and the way that I did it, I started out being interested in the type 3 bursts, and then everything else that I talked about just came serendipitously out of this data set. Those, for the type 3 bursts, you want a very fast time resolution because they happen on really short time scales. So I was imaging 5-minute chunks of data at our maximum time resolution. For this public data set, the plan is to reduce images more at a resolution of maybe at 1 image every 3 seconds or so, and try to sample at least 1 observation for every day of observing. So that's going to be around a year's worth of days, but spread between mainly 2014, 15, and 16. So that covers phase 1 MWA, and then phase 2 will be another beast in the future because the calibration procedures have to be tweaked a little bit to work with that data. So hopefully, we're hoping, it depends on the success of these proposals, but we're hoping that we might be releasing images to the community in a year or so, maybe a year and a half.
I do have a question.
Sure.
You're comparing your observations against a potential source surface forestry model.
Yep.
How well do you trust that model to actually be right?
So good question. My understanding, I don't know that much about the modeling, to be honest, but my understanding is that as you go to larger and larger heights, the field tends to look more and more potential. So at the heights that we're looking at, I think the potential field is probably pretty good, at least for the lowest frequencies. At higher frequencies, that's when it starts to become less and less reliable, and you would want, because you're looking deeper and deeper into the corona, and you would ideally want to use some other model for that.
And that's where you're seeing the discrepancies.
At the higher frequencies. Yeah, although we're seeing such huge discrepancies between. So I'm not sure. It could be because of the model. Although I don't know. My feeling is that you probably have a mixture of emission mechanisms, and that that's going to be the challenge, to disentangle the different emission mechanisms. But we're not sure.
Sure, go ahead.
What sets your field of view? Can you go wider, or is there just nothing to see out there?
Oh yeah. So the MWA is a wide field imager. So all of these observations, when I first make them, start out with a field of view of like plus or minus like 15 solar radii, something like that, and that can go wider too. You can basically observe the full sky at any moment. So yeah, one of the things we're hoping to do with wider field images is if you can get your calibration solutions finer than we have with these data sets, you might start to be able to see some of the background sources in the vicinity of the sun. This is something that actually has just recently been achieved with that other data reduction pipeline called AirCars. They can't do the polarimetry yet, but hopefully we're hoping to merge things and be able to do that in the future. And if you can detect background sources right next to the sun, then you could have a CME, and that could be occulting a linearly polarized source right next to the sun, and then you can make a Faraday rotation measurement through that and derive the field strength and orientation of the CME. That's like one of the main goals that we would really like to be able to do with the MWA.
Have you completely positively excluded the possibility that the opposite sign of the polarization in the ring could be just a calibration offset?
So the short answer is that we have tried very hard to do that. Completely, positively, 100%, that's hard to say. But this feature that we're seeing, we only see, at least for as far as that ring structure with the coronal holes, we only see an association with coronal holes. And they rotate with the sun as you expect them to. Often at the lower frequencies, the total intensity signature of a coronal hole can look basically like an active region noise storm source does, and you never see that effect with the noise storm sources. For those reasons, and to the extent that we have investigated the calibration effect, so we tried to reduce that data set with both of the pipelines. And for the total intensity, we get identical results. We can't do an independent calibration for the polarization yet because only one of the pipelines can do the polarization at this point. But because of the consistency that we get in the total intensity, because of to the extent that we've dug into the calibration solutions themselves, and because of how frequently we see this, how they behave and how they don't behave for other sources, we're pretty confident that it's a real effect. At least I am.
Anyone else? If there's no more questions, let's thank you.
Thank you.